Hello physics students. In this video, you're going to learn how to find the magnetic field of a complete ring of current. Now remember, in the last Biot-Savart law video, we figured out, or you learned how to find the magnetic field of an arc like this. The current came in here, went around the arc, and then exited here. So it was like a partial circle, and you found the magnetic field at the center of curvature. Today, the ring will be complete, and the current will go all the way around in a circle. We'll first find the magnetic field at the center again, and then what we're going to do is find the magnetic field with a second calculation along the axis out of the plane of the circle out here. So let's begin with the first case, the magnetic field at the center of a ring. So Biot-Savart law 3, the ring of current. A, find the magnetic field at the center, and we've got a current I as indicated here, and this ring has a size of radius capital R. So we use the Biot-Savart law. Here it is written out as an expression, but first what we need to do before we move on is figure out the direction of the magnetic field from right-hand rule number 1. So what I want you to do is do that now. I'm going to create a pause, figure out which way the magnetic field goes at this point over here, caused by this little ds of the current. So go ahead and do that now. Okay, this is what you should have done. You should have not used this right-hand rule, which is the one for force on a moving charged particle through a magnetic field, but this one, the current and magnetic field. So if I put my thumb in the direction of the current here, then I see my forefingers come out of the board. So 90 degrees to the radius vector, we've got a magnetic field coming straight out of the board. So I put a dot here instead of an X to indicate out of the board. Next, I realized that I have to apply the Biot-Savart law and then add up, or in other words, integrate the contributions to the magnetic field here from all the ds's going around the circle. So do I need to multiply by a trig function to pick the proper component because of the integration? The answer is no. If I repeat the right-hand rule for part of the a little ds of the ring here, then you see that my forefingers again come straight out of the board. No matter where I am on the ring in my integration, my eventual integration, magnetic field always lines up with all the other magnetic fields. So I just need to fill in the pieces here and then integrate. So similar to the process we did in the last video, all that's going to change are the limits in this particular case. So what angle do I plug in here? Well, remember that the angle in the Biot-Savart law is the angle between the radius and, well, that looks sideways. Maybe that'll confuse you. And the ds. So ds goes this way, radius that way. No matter where I am in the integration, there's going to be ds like this and radius like that. It's always, theta is always 90 degrees in the Biot-Savart law, so I plug that in. Also, I substituted in lowercase r for capital R, which is the radius of the ring in this particular case. So now there is the length of that tiny vector dB. I don't want just the contribution of one piece, I want the magnetic field of the entire ring. So I have to now add those pieces up. In other words, I have to integrate. But before I do that, I'll create a pause to allow you to copy this down. Okay, so moving on, we have, we're going to integrate, so we have to realize first that all the variables are constant over the integration. Mu 0 I, 4 pi, and r squared, I took them all out of the integral. All that's left integrating is ds, the arc length. And so I think about, well, what does S start at and end at when I integrate completely around a circle? Well, I start with 0 arc length and I go all the way around. In other words, the circumference. So yesterday's video, we had some other theta, like maybe pi over 2 here for maybe a quarter way around the circle. No, today it's the whole way around. That's all that changes. And then we integrate ds to s for these limits, plug them in, and solve. Now, unit check. Really don't even have to do that. We got mu 0 amps over meters, so the units check out. Again, if I'm missing a constant, I wouldn't catch it, but if I had r squared here, I could catch that mistake. So let me create another pause to allow you to copy this down. Okay, that was example 1. Now we're going to move on to example 2, finding the magnetic field on the ring's axis. But before I begin, I first want to give you a little warning. In some ways, this example is one of the hardest things that we do all year in this course. And the reason why is because it's very highly involved in all 3 dimensions. Now, we've been thinking and analyzing things in 3 dimensions all year, but never to the extent of this problem. It's hard to think through all the components and all the directions of integration, but it's also even hard to draw what's happening in such a way that it can guide your analysis. Now, to help us or help you see and understand what's happening, I have a little model here. So let me bring it into view. What I have is just a simple bucket with a dowel coming out through the center of the bucket. This represents the ring of current, the top edge of the bucket. This is the axis that we're talking about in this diagram. So we have current going around this rim like this, okay? And we want to find the magnetic field up here. So the first thing is we start with the Biot-Savart law. Mu 0 I ds sine theta 1 over r squared, and I put theta 1 because there's going to be another angle in this problem. So filling in the pieces, this angle, what is the angle we plug into the Biot-Savart law? So here comes our first challenge. So the current is running, suppose, along the rim like this. The angle is between this current and the radius vector, which I'll use this, in carpentry we call this a framing square, a little framing square. So it's the angle between this current right here and the radius vector. So the radius vector is this metal right here, current like this, and if I go like this and tilt this up to your view without changing the angle between this metal and the current ds, you see that it's 90 degrees here. And that's the same angle no matter where I am when I ultimately integrate. As I'm integrating around over here and I go like this, I've got ds and radius. If I bring this into your view without changing the angle down here, you see once again we've got ds and r 90 degrees to each other all through the integration. So that's why I filled that in as 90 degrees. And then the r. The r is how far away this little bit of current is from the point we're trying to find the magnetic field at. And that is from the Pythagorean theorem, this r squared is capital R squared plus x squared, right? These two legs squared equal the hypotenuse squared. So that's the length of the dB, which I haven't drawn yet. That's the next thing we have to do, is figure out the direction of the dB, so then when we start visualizing our integration, we'll be able to see, is there a component that cancels, is there a component that doesn't, or do all of them align like in this example? So, once again, suppose we've got current coming here. Here's my radius vector, and the reason why I use this square is because my choices for the dB are either the way I have them, this part of the square, so it's an arrow going like this, or it's an arrow going like that. I have to use my right-hand rule to figure that out. Okay, so if I put my thumb in the direction of ds, then my 4 fingers show the direction of the swirl of the magnetic field. So it's going around this ds like this, okay? So at this point, if it's swirling around like this, it has to be like this, not 90 degrees that way. That would be if the current were going the opposite way. So that's the dB that I draw. On this diagram, I put my thumb in the direction of ds, and again, it's a little hard to draw this in 3 dimensions. So an alternative that, if this is confusing you about which way ds goes, you could also draw this ring instead of how I drew it like this, but like this. And this would be a cross section if you didn't have the ring at an angle like I had like this, right? Then it looks like an oval that I have. But if I tilted it all the way around like this and you're looking at it dead on to the side, then if you look at a cross section of the ring, you would see we got wires up here and wires here. So this is like the ring. And the current is going out here and going in here. And then we could see that the dB would go like this by the right-hand rule. So that's a little easier to see. So if you want to change your diagram to have it drawn this way because it'll be clear, go ahead and do that. Again, this is all what's going to be easiest for you to understand. So here's my radius vector. And as I said, we got to have the magnetic field perpendicular to that. So I could use my framing square nicely and draw a, well, a little tricky with a marker. Okay. So, oops, lost my wire here. So there's the dB by the right-hand rule, length given by this expression right here, okay? All right, now I have to imagine that I know that I don't want just this. I want the entire magnetic field for all the DS's around this ring. So we're going to obviously have to integrate. But I need to first create a pause for you to catch up if you need to with these diagrams and the Biot-Savart law expression there. So go ahead and do that now. Okay, so now the visualizing of the integration. As I'm integrating around this to get all the magnetic field of all the pieces combined, what you have to realize is that as I'm integrating around, eventually, see how this vector goes up in this direction? I'm going to get in my integration over here, creating a magnetic field going this way, the same length, and those components will be the same. The only difference is that the vertical components will align here and here, up and up. But the horizontal components, one is going toward your right, and over here from this ds, it's going the magnetic field to the left. So these components, what's looking horizontal here, but on my drawing over here will be the vertical components, they are going to cancel. So what I really need is this x component. Okay. So I need to know what this angle is here, theta 2. Because with this being a right triangle, I can now say that the dB in the x direction will equal the dB along the hypotenuse times the cosine of theta 2. So we've got another angle. Okay. So the other thing that we have to realize now is that this theta 2, we can figure out where it belongs in this triangle. Now, if this is 90 degrees, that means these two are complements to each other. They add up to 90, which means that this angle and this angle up here are the same right there, theta 2. And so I can fill in what these pieces are. By taking that whole expression. I may have to, I think I'll need more room here. So that's the dB. And the cosine if you go back to this triangle right here, the cosine will be the adjacent side over the hypotenuse. The adjacent side being capital R. And the hypotenuse will be the square root of these two squared added together from the Pythagorean theorem. So it's this over that being so there is cosine theta. All right, so now that's this dBx caused by that ds. But I don't want just, actually, you know what? Before I mention that, let's touch this up a little bit. So I'll put everything on the top together. And on the bottom, we have this. And then to the 2 over 2, and the 1 over 2 gives us 3/2. All right, so again, this is dB in the x direction. So as I was saying, we don't want just this one arrow caused by this little ds. We want all the dBx's added together, contributed from the entire ring. So that means add, add, add. In other words, integrate. So I've got to integrate this to get b in the x direction. I'm going to leave space for the limits. And okay. Now, what are the limits? Well, again, I'm integrating the arc length. And I'm integrating around a circle. Once again, the limits are 0 to 2 pi r around the ring. All right? All right, so if you need a moment, I'll create a pause to allow you to copy this down. Okay, let's move on. Move this table out of the way. Just fix the lamp over here. And let's, so if you look at this, when you're integrating, you should realize that all of these terms are constants, even x, because as I integrate around here, around this hoop, the x-coordinate of my point in question is the same no matter where I am in my integration process. So the only variable that we're integrating is ds. So once again, our integral is surprisingly simple in this case. Mu 0 I r So the integration in this case is trivial, easy. When I said this was a hard problem, it was because of the visualizing and figuring out what all the angles are in the components. That's the hard part. The integral is not. All we have to do now is just plug in our limits and simplify. And what's left is oops. The 2 pi and the 4 pi leave us just 2. Okay, so let me create a pause to give you a chance to copy this down if you need it. Okay, before I move on to one final thing, I just want to do a unit check because now this formula is considerably more complicated than the others that we've learned so far. So what we have to do is compare it to B equals mu 0 I over 2 pi r, the basic formula we learned for the magnetic field around an infinite wire. So we need a mu 0 in amps over a meter. Is that what we have here? Well, we have our mu 0 in amps from the mu 0 I. Then we've got meters squared in the top. And in the bottom, we've got meters squared to the 3/2 power, which gives us meters cubed, which simplifies to mu 0 amps over meters. So the form of the formula looks correct. The next thing, it's often customary, actually before I talk about the graph, another thing I want to point out is that this formula is a generalization of the one we learned in example 1. What I mean by that is once you have this, you actually technically don't need to know how to do example 1, even though it's easier, because you could just take this formula and plug in x equals 0, which would be the magnetic field at x equals 0 is here, the center of the ring. And so this should give us the same answer that we got in example 1 if we were to plug in x equals 0 here. So what happens? Mu 0 I r squared over 2. If you plug in x equals 0, you have r squared to the 3/2 power, which is just r cubed, and it simplifies to the same formula we had in example 1, as it should. So the last thing is sometimes you're required to sketch these functions, so could be possible in this case too. This is the magnetic field. This is the x-axis. If you look at this, at x equals 0, the magnetic field at x equals 0 here is that value, mu 0 I over 2r. And then this graph, what happens is as x gets bigger, this denominator keeps getting smaller and smaller. So this is a maximum, and the function sort of decreases in some kind of form like this. Furthermore, if you plug in negative x, you get the same bx value. So it's basically an even function, so we should have like a mirror image here for negative x. Okay? You can also figure that out from the right-hand rule, that if you did the magnetic field up here, it points like this with a component away. If you did it down here, you would see that it also points in the same direction back here towards the center of the hoop. So you could figure that out from the formula or the right-hand rule that this is a mirror image over here. So I'll create a pause to give you a chance to sketch that graph. All right, so that was Biot-Savart Law 3. Very challenging, but very rewarding when you get that ring example. Remember, Biot-Savart Law, you use the formula, mu 0 I, mu 0 I ds sine theta over 4 pi r squared. You use that to find the length of the dB, then you use this right-hand rule to find the direction, and then you integrate, possibly picking a component if necessary, and you integrate around the ring. That was the general process. Very difficult. Example 2, go back. When you finish watching this, look over the main points, study it, because it is something that you might have to do on the AP. All right, I hope you enjoyed the video. I'll see you in the next video.